today in this webinar series, we have a invited speaker, Dr. Patrick Martin from Nanyang Technological University, Singapore. Dr. Martin obtained a BSc in biology from University of York in UK and PhD at National Oceanography Centre, Southampton, UK. He then did postdoctoral research at Woodsole Oceanographic Institution, USA, and Nanyang Technological University, Singapore. He is now an associate professor at the Asian School of Environment, Nanyang Technological University, and he has worked on topics ranging from open ocean carbon fluxes, phytoplankton nutrient physiology, phosphorus cycling, coral core paleoproxy reconstructions, to coastal carbon and nutrient cycling. A major focus of his research is the land-ocean flux of organic carbon and its biogeochemical processing in the coastal seas. In today's talk, Dr. Patrick will talk about his ongoing time series research in the Singapore Strait, where he and his team have been measuring carbon dynamics since 2017. So with this brief introduction, I would invite Dr. Patrick Martin to deliver today's webinar. Welcome.
Okay, thank you very much, Amit. Thanks for the introduction and thanks very much for the invitation. And also thank you everybody for turning up fairly late on a Wednesday evening. It's great to see a good turnout of carbonate system enthusiasts. So as Amit was saying, I'm going to be talking about the coastal carbonate system dynamics here in Southeast Asia with a focus on our time series work in Singapore. I wasn't totally sure how much of a specialist versus generalist audience to expect. So I wanted to start off giving just a very quick general introduction to make sure that everybody is on the same page in terms of the carbonate system. So what we mean by the carbonate system is really the chemistry of dissolved carbon dioxide and the acid-base buffering system of seawater. And now this breaks down into four main measurable parameters. And the nice thing about the carbonate system is that as long as we measure any two of these, we can calculate everything else about the carbonate system. And these four main measurable parameters are the dissolved inorganic carbon concentration, the DIC, which is the sum total of the species shown here in my diagram, the partial pressure of carbon dioxide specifically, so that's just this dissolved CO2 part here on the left, the pH, which is basically the proton concentration, as well as something a little more esoteric that we call the alkalinity. And by alkalinity, essentially this is the pH buffering, so it's the total of all of the proton accepting anions in seawater. Now, you don't need to remember and worry too much about these definitions, but just keep these four main parameters in mind because we'll be looking at these in future. Now, the other part of this general introduction is why do we actually want to study the carbonate system? And of course, on the one hand, that is, because we're marine scientists and we get curious about things. But much more importantly as well, the carbonate system fundamentally controls the strength of the oceanic carbon dioxide sink. It controls the seawater pH. And that means that it has a very large impact on marine organisms, in particular on calcifiers. So things like coral reefs are extremely sensitive to pH or to the calcium carbonate saturation state. And of course, all of this is happening against the background of long-term ocean acidification due to human carbon dioxide emissions. So because of our emissions, the average pH of the surface ocean globally has already measurably decreased. And depending on which emission scenario we follow in future, it's projected to decrease further. And this can be modeled. Now, across the open ocean, we have comparatively fairly well-established monitoring systems from a network of time series sites across the ocean. And it's in some ways easier, I think, to model and predict the evolution of the carbonate system in open ocean systems. So we've got quite a number of multi-decadal time series that have been around for quite a long time. This is just showing a selection of those, and we can see in all of these where we tend to see pH decreases long-term. There's some regional variation there. There's also regional variation in how much the pH changes over shorter time scales. But the main drivers of this are human CO2 emissions, which are driving the long-term decreasing trend, as well as then natural oceanographic processes to do with physical ocean circulation and biogeochemical variability. Now, in contrast to that, when we get close to the continental margins and we get into coastal waters, we face a lot more complexity because the coastal ocean additionally has large inputs of substances from land, which are partly natural and partly anthropogenic. And usually, because of the greater productivity of coastal waters, we typically have much greater rates, so much faster rates of carbon cycling. So the factors that come to play are, for example, eutrophication from nutrient input, extra carbon dioxide production from the breakdown of terrestrial organic matter, as well as naturally, and then of course with eutrophication, unnaturally stimulated high rates of photosynthesis, respiration, as well as also calcium carbonate production and dissolution. And now these biogeochemical processes, when we think back to the parameters of the carbonate system, the alkalinity, the DIC, and the PCO2 and pH, these biogeochemical processes create predictable variation in the carbonate system. So photosynthesis, which removes carbon dioxide, or emission of carbon dioxide from the ocean into the atmosphere, will decrease the DIC concentration, have little to no impact on the alkalinity, and therefore reduces the PCO2 while raising the pH. And the opposite of that, when there's respiration or CO2 uptake by the ocean, it does the opposite. The DIC concentration increases, the alkalinity shows little to no change, the PCO2 increases, and the pH goes down. And because there's so much additional complexity in coastal waters, and we have fairly high rates of these biogeochemical processes, within coastal waters, the biogeochemistry can either mitigate or it can actually enhance the impact of ocean acidification from the global long-term CO2 emissions. So I think that's exactly what motivates many of us here in the room, and we think that there's a strong need to have more coastal time series observing. Now, in Singapore, we started off some of this work initially with very little funding and very basic techniques limited to just a few biogeochemical parameters, not yet really working on the carbonate system. But then starting from about 2017 and 18, we were able to start getting really serious about this. So we then started up a monthly program of biogeochemical measurements. This included carbonate system measurements. And now since 2023, with a new project, we actually have, we're starting to put out sensor-equipped moorings, of which the first one has been in for nearly a year. And of course, to do this, obviously, we need funding. So we've been funded from some of the research funders here in Singapore through various schemes. Now, welcome to Singapore for those of you who have not been here before or have only passed through, perhaps. We're located here in the central part of the Sunda Shelf Sea. And of course, a key feature of our oceanography is, like in other parts of South and Southeast Asia, we have a reversal of the ocean current due to the monsoon season. So in the northeast monsoon, we've got water from the South China Sea pushing out towards the Indian Ocean, and then the southwest monsoon that reverses. We've got regionally fairly high rainfall because we're in an equatorial location. And another important factor that I want to highlight already is that the area is home to very large areas of peatlands, of tropical peatlands. And the rivers draining these peatlands here in Southeast Asia actually account for approximately 5% of the global flux of land-to-ocean organic carbon input. So this kind of sets the background for us against which we need to interpret the biogeochemical dynamics, including of the carbonate system. But before we get into the carbon chemistry, let's start off with a bit of the physics and look at salinity. So this is our monthly data for surface water salinity in the Singapore Strait. And I've color-coded these for handy reference according to the monsoon season, so southwest and northeast monsoon, as well as the intermonsoon seasons. And we can see there's a very clear feature over multiple years. The southwest monsoon has the lowest surface salinity. The northeast monsoon also has a bit of a decrease, but the southwest monsoon is really where the main drop in salinity happens. And that's interestingly, even though the southwest monsoon is actually less rainy than the northeast monsoon. So the way we explain this is that this is linked to the hydrography and to the physical oceanography, where during the southwest monsoon, the waters that flow through the Singapore Strait are coming from the already freshened waters in the Malacca and Karimata Strait, versus during the northeast monsoon when we get the more open South China seawater influence. There's also, now that we've got multiple years of data, we're starting to recognize that there also seems to be quite significant interannual variability, which I'm not going to be talking about so much today, but it's something we're starting to focus on. So what then about the carbonate system parameters? Now, when we look, right, remember we've got four main variables, and the two that we really like to measure because they're straightforward to do in the lab are the alkalinity and the dissolved inorganic carbon, the DIC concentration. Now, when we look at our data, and for these we started in 2018, we can see more or less both alkalinity and DIC are approximately tracking the change in salinity. So lower salinity during the southwest monsoon equals lower alkalinity and lower DIC. And this makes sense because in many ways, DIC and alkalinity tend to actually behave fairly conservatively. So they're often showing fairly good relationships to salinity. And this pattern is kind of, in many ways, what we would expect to see. Now, this kind of, for now, just looking at this data set, it looks a bit uneventful. So we're just finding an impact from fresher or saltier waters, depending on which way the current is going. But we get a sense that there's something more interesting going on when we plot this as the ratio of DIC to alkalinity. And when we plot that ratio, we actually see that the amount of DIC relative to the amount of alkalinity actually also shows quite strong seasonal variation. So during the southwest monsoon, again, we get higher levels of DIC relative to alkalinity than in the other seasons on average. And now if we think back to our plot, right, of how alkalinity and DIC vary, how that impacts the other carbonate system variables, and what processes are driving this, it's fairly easy to see that an increase of DIC without a corresponding or limited corresponding change in alkalinity probably points towards inputs of carbon dioxide into the water from something like CO2 invasion or respiration and organic matter breakdown. And that, of course, indicates that the PCO2 and the pH probably change and show quite dynamic behavior as well. And when we look at the, when we do the calculations for the carbonate system, we see that exactly that is also, in fact, what we observe. So the top panel here shows the monthly measured seawater pH on the total scale. And just focusing on the top panel first, we can see very clearly during the southwest monsoon, we also get a strong seasonal decrease in the seawater pH. typically by about 0.1 to 0.2 pH units relative to the other seasons. Again, sure, there's interannual variability, but the seasonal trend is very clear. Now, within the carbonate system, once we've measured two of our main 4 parameters, we can calculate a whole range of other properties of the carbonate system. And what the bottom panel shows you here is the saturation state of aragonite. So that's the form of calcium carbonate that's precipitated by corals, as well as also by some planktonic organisms like pteropods. Of course, here in tropical Southeast Asia, in coastal waters, we're typically particularly concerned about corals. So that's why aragonite is often something we're interested in looking at. And we can see that just like the change in pH and the change in alkalinity and DIC, we see a strong seasonal decrease in the aragonite saturation state. So the southwest monsoon quite typically has values for the aragonite saturation state of 2.5 or even as low as about 2. And so essentially, we think that the lower the aragonite saturation state is, especially when it starts to go below values of about 3, the more difficult life becomes for calcifying organisms. So again, if we think of things like corals or so, the lower the saturation state is, the more energy has to be expended for them to build their calcium carbonate skeletons, and the more an entire reef system will start to be more prone towards net dissolution as opposed to net calcification, just from a purely chemical point of view. So this is very interesting. When we started recognizing this, of course, you know, we've clearly got a very large seasonal variability in the seawater carbonate system here. We think you know, the proximate explanation is, of course, that there's this hydrographic shift, which brings different water masses into the Singapore Strait in different seasons. But we're still interested in understanding what is the ultimate explanation, i.e., what are the drivers in terms of the carbon cycle that are leading to more concentration of carbon dioxide during the southwest monsoon. So clearly, we've got some kind of biogeochemical process that is delivering extra CO2 into our waters during the southwest monsoon. And the most likely explanation is that there must be additional organic carbon getting remineralized within the shelf sea waters. Now, of course, think back to when I'd introduced Singapore. I'd given a clue saying that we're surrounded, or at least very close to the major peat deposits in Southeast Asia. And these peatlands account for a very large input of organic carbon to our coastal waters, which is overwhelmingly in form of dissolved organic carbon, or DOC. Okay, so DIC, dissolved inorganic carbon, DOC is the organic matter that's dissolved in seawater. And so this already gives us some hint for what we should be looking for. You know, maybe this peatland DOC is starting to get decomposed to CO2 by some kind of set of processes. But all we are seeing, all we're able to measure here is carbon in seawater. You know, we can measure it as a total concentration. But to try and identify whether this DOC is actually coming from peatlands or not, we have to get a little bit more sophisticated. And in particular, a great way to try and tease apart where or which different types of sources are contributing to carbon is to look to carbon isotopes. And in this case, we're looking at stable isotopes, so the delta 13C. And we see quite a strong discrepancy, or quite a strong difference rather, in the delta 13C of organic carbon that's produced either by photosynthesis on land with a more negative signature, or a less negative signature if it's produced as autochthonous organic matter in the marine environment. So handily, when we started our time series, we immediately recognized that it would be good to not only measure a few carbonate system parameters, but also try and measure plenty of other parameters to help explain the dynamics that are going on. And what you're looking at here is scatter plots, again, color-coded by the season over multiple years, where on the left plot, I'm plotting the delta 13C of DOC in our waters against the DOC concentration. And with the delta 13C, a more negative value points towards an increasing contribution from terrestrial carbon, a less negative value towards a greater domination by marine carbon. And then I'm also plotting in the right-hand panel the delta 13C of DOC against something a little more esoteric that's called the colored dissolved organic matter, or CDOM. And essentially CDOM it's the light absorption or essentially the color of the organic matter. And typically organic carbon that washes out of soils into rivers and out to sea tends to have a high value of CDOM. So lots of CDOM means of more terrestrial origin, less CDOM means typically associated with more marine organic carbon. And we can very clearly see that our southwest monsoon data tend to cluster in the areas of our plots with fairly high dissolved organic carbon concentration and fairly negative delta 13C of DOC, while also being associated with fairly high quantities of CDOM. So all of this is very clearly pointing towards a significant input of terrestrial dissolved organic matter during the southwest monsoon. So, you know, looking at the map, you might hypothesize that there should be a peatland influence. And in fact, with our data and the isotope composition and the carbon concentration, we can in fact confirm that peatland organic matter is a significant contributor during the southwest monsoon. Now, this is all very well and good, but we also need to find out whether this terrestrial organic carbon is actually getting converted into inorganic carbon. Because if it isn't, if it just sits there in organic form, then there won't be very much of an impact on the carbonate system. So to understand that, we need to then also measure the delta 13C of the DIC. And basically, if the delta 13C of the DIC becomes more negative, that indicates that there's an increasing input of carbon dioxide that's been formed as the breakdown product of terrestrial organic matter. So lower delta 13C of the DIC means a greater terrestrial contribution to the CO2 production. And in fact, that's exactly what we see. So during the southwest monsoon, again, the delta 13C of the DIC is also becoming more negative, indicating that this excess CO2 source is indeed coming from the decomposition of terrestrial organic matter. Now, when you're measuring isotopes and concentrations of things, you can actually get quite quantitative. And I'm not going to go into that now, but if you're interested, my former PhD student, Yongli, did a very nice quantitative analysis of that. I'll have the proper reference to the paper at the end of this talk. Now, we can also go and make scatter plots then with our data, plotting the delta 13C of DIC, so where we think lower values of this from the input of terrestrial organic matter breaking down into CO2 is probably the driver. We can see that this delta 13C of DIC is indeed also significantly correlated with pH, as well as with our aragonite saturation state. So we think indeed this seasonal acidification that we're seeing, and it is of course on the one hand linked to the water masses moving in and out of the Singapore Strait, is in an ultimate sense caused by the decomposition of terrestrial DOC into DIC within our shelf sea. So just to summarize then these seasonal dynamics, we see quite a strong seasonal carbonate system variability. And this is largely driven by the combination of the current reversal, as well as the fact that we've got the input of the peatland DOC and the decomposition of that DOC into CO2. After that decomposition has happened, then the ocean currents can carry this, when they reverse direction, can carry the CO2-rich water from the Malacca and Karimata Strait areas back through into Singapore. Now, I'd said when I showed the salinity time series already that we're also, in fact, seeing fairly interesting interannual variability. So I'm showing here again the salinity time series, so we can see that in some years the southwest monsoon has a lower salinity associated with it, in others a higher salinity. Now, I don't have a lot to say about this yet, because this is very much something that is work in progress. We think that this is probably driven by a combination of interannual changes in rainfall and interannual variability in ocean circulation. So this is something we're currently working on together with both climate data as well as a regional shelf seas ocean model based on the Hamsom or Hamburg Shelf Ocean Model. So the bottom panel here shows some data of monthly mean water transport through the Singapore Strait generated with the Hamsom. So my team members Yuan and Bernhard are currently working on that. One thing that I still want to highlight before moving on to the more shorter term dynamics and the high frequency monitoring that we're doing now is that the salinity data I'm showing you at the top here are all based on monthly spot measurements. And this goes also for most of our carbonate system measurements that I've shown so far. So once a month, we take a boat out, we take a water sample, we analyze that, or for the salinity, we do a CTD profile, and then we record the value and add it to our time series. Now that we have had an actual monitoring buoy, with a proper mooring and real-time data acquisition at minute frequency, we're starting to see that, in fact, we also clearly get quite a bit of variation within just a time scale of a month. So this is being rolled out, these data sets are being rolled out at the moment through a dedicated website, and I've got the link again towards the end. This just shows you the first nearly year of data for salinity. And we can see that even just within January or February or March, we're getting variability of perhaps up to a PSU. So I think in contrast to going out once a month and just collecting a water sample on that monthly basis, having high frequency data, I think, is really, really valuable and important to get better accuracy for even also for our long-term variability. Just to show you what this looks like underwater, this is photographed on the day with particularly good visibility. The Singapore Strait is perhaps not known as the top destination for divers, but here's our main sensor package under the buoy. Then we've got additional modules, in this case here for the PCO2 sensor. And as I say, the data are transmitted in real time. Now, when we're able to measure carbonate system measurements at very high frequency, so at the level of minutes to hours, and also collect other data with that, we can actually start to see daily changes that are caused by the daily cycle in photosynthesis and respiration within the water. So during daylight hours, we get net photosynthesis, and the PCO2 of the water goes down, the oxygen concentration of the water goes up, and then at night, there's net respiration, so the PCO2 goes up again, the dissolved oxygen concentration decreases. So the top here shows us the PCO2 variability, I think at approximately half-hourly frequency, and the bottom shows the dissolved oxygen concentration. And we can very clearly see there's very nice correlated diel cycles. We've had some problems with getting pH sensors up and running, partly to do with company supply chain issues. I think anybody who's tried to do pH sensor-based measuring for measurements for monitoring will be able to sympathize with this. Hopefully from next year onwards, we'll be able to get pH integrated into this as well. Now, this is, of course, very exciting because the magnitude of this change in principle is related to the magnitude and therefore to the rate of daily photosynthesis and respiration. So from data like this, we will ultimately, I think, be able to estimate net productivity in the water column. But before we get to that point, we have to do a lot of very careful quality control on high-frequency buoy data like this. And of course, we can collect great data with buoys, but we have often very significant problems related to factors such as sensor drift, degradation of the sensor parts, and the big one for us here in our tropical waters is biofouling. So this data set here shows you the high frequency measurement over a period of multiple months. The top panel shows the PCO2, the bottom one, the dissolved oxygen concentration. And on the top panel, the cross data are the calculated PCO2 based on our laboratory alkalinity and DIC measurements. So we treat those lab data as essentially the gold standard for referencing against and to check to do the quality control for the sensor. Now, once we exclude a couple of data points where we know we had significant baseline drift or major fouling problems, I think we actually do fairly well in that data validation. But we can also see that we get plenty of variability or plenty of times where we get very strangely high periods of diurnal variability. And essentially, or especially when we see large variability starting to crop up in one sensor, but not in the other, that's a bit of a red flag and usually related to biofouling problems. So with biofouling, especially, not all sensors are created equally. So here I'm zooming in on a 1.5 month period in September and October of this year. And the top dots again here show the PCO2 in the water. The crosses are our lab validation measurements. The magenta dots down here are the dissolved oxygen. The nice thing about the oxygen sensor is that we have a wiper part that wipes away the biofouling. So the oxygen is much less susceptible to fouling, but we can see we've got a period here in early October where the PCO2 sensor, starts to show very, very high levels of diurnal variability that are not matched by the oxygen sensor. And then once we went out and cleaned the sensor, we're immediately back down to more sensible ranges of variability. So I wanted to put these slides in just to highlight the challenges in actually making sure that when you have sensors in the water on long-term moorings, to ensure that the data are actually valid. And clearly for the PCO2, this period in early October has to be disregarded as probably affected by biofouling. Now, the reason I think it's really worth, though, to put in this effort and to persevere is because once we get to grips with these factors, we can really start to tease out the metabolic impact. So from the net production and respiration, net calcification or dissolution on the carbonate system at daily, at the level of diurnal variability. Now, I'm showing data here that we collected previously from sensor deployments that we ran before the buoy was in the water, so before we had real-time telemetry, but over the period of 2017 to 21. And when we take those data and we look at the daily change in pH and the daily change in dissolved oxygen, we can again very clearly see a metabolic signal. So the pH changes because respiration at night is producing CO2, photosynthesis during the day is removing CO2, and because of this respiration photosynthesis change from night to day, of course, we see a change in the dissolved oxygen concentration. And these two are very nicely correlated. But there's a subtlety to this, which I think is important for exactly how the pH and the carbonate system respond to this metabolic variability. And that's to do, again, with a somewhat more esoteric aspect of the carbonate system called the buffer capacity. So by the buffering capacity, there are a number of ways to define this, but the way that I want to think about it now is how much does the pH change for a given quantity of dissolved CO2 being added or removed from the water. And this buffering is in large part due to the concentration of carbonate ions in the seawater. So when we add a little bit of extra CO2 into the water, either from metabolic processes or from ocean acidification or from peatland organic matter decomposition, this CO2 will react with water to give us bicarbonate and a proton. Okay, so hence the pH will decrease. But some of these protons that are being produced actually react together with the carbonate ions and get neutralized. So when we add a certain quantity of CO2 into the water, we actually tend to observe less of a change in pH than you might expect just based on the CO2 to bicarbonate plus proton reaction. However, there's only a finite concentration of carbonate ions in the water. And as we add more and more and more CO2 into the water, we erode that buffering capacity because we've already depleted more and more of the carbonate by having already previously reacted it with protons. And now again, we can go to our time series in Singapore, where we have this large change seasonally in the carbonate system. And we can actually see that not only do we see a change in pH and the carbonate system parameters of the alkalinity and DIC, but we also see quite a significant seasonal change in this buffering capacity, meaning that during the southwest monsoon, we get a larger change in pH for the same quantity of change in CO2 concentration than we do in other seasons. And if we go back to our older sensor data, where we had the pH sensor and the oxygen sensor in the water, I think we actually see an impact of that seasonal change in buffering capacity in as much as during the southwest monsoon, we actually see the largest daily change in pH, even though the change in oxygen concentration, so the metabolic driver of this carbonate system change, is actually lower during the southwest monsoon than in some of the other seasons. So in other words, during the southwest monsoon, a given quantity of photosynthesis or respiration has the potential to impact the pH more than in the other seasons. Now, I think this has an important set of implications if we think longer term, how will the carbonate system continue to vary? And if we go back to our map and think of the regional physical oceanography, the annual mean flow is every year that water moves from the South China Sea on average out towards the Indian Ocean. So of course, we've got the seasonal reversal, but we've got more water flowing from the South China Sea into the Indian Ocean than the other way. And now the South China Sea tends to have a PCO2 value that's fairly close to atmospheric equilibrium, which means that as the long-term global ocean acidification due to our human CO2 emissions is increasing, that source water that we're getting here onto the shelf that's coming out of the South China Sea is going to arrive with increasingly higher levels of prior acidification. And that means that the initial buffering capacity of this water flowing onto the shelf is also going to become lower, which means that I think it's likely that we're going to see in future an amplified pattern where the long-term open ocean acidification, as well as our on-shelf processes, are going to be amplifying each other, such that we'll see greater seasonal variation and also greater diel changes in the carbonate system from our in-water metabolic processes. So this brings me to my conclusions. I think all of us can appreciate that the coastal carbonate system is very variable, and it's also quite complex. And it's driven in different parts of the world and in different coastal areas by quite different factors. So here in Singapore, we've got large seasonal changes as a combination of our regional ocean currents, as well as then the remineralization of the peatland dissolved organic carbon that enters the shelf sea. We then, on top of that, have diel variability due to community metabolism. And probably the pH change that we're getting is already amplified by seasonal changes in the buffer capacity due to the peatland organic matter degradation. We clearly have interannual variation, and as I say, this is very much work in progress because you have to have enough years of data before you can say much about it. So ask me again maybe in a year or two and then down the line. And I think it's really important that we have more long-term coastal observatories, both for carbonate system parameters as well as also related biogeochemical parameters. And of course, I've highlighted the fact that these kind of sensor-equipped systems really need a lot of careful, sustained quality control. So lastly, thank you all for your attention. And of course, it takes a big team of people and a lot of collaborators to pull off something like this, and especially with the moorings. That's only possible through a large multi-institute collaboration that involves colleagues from our other institutes here in Singapore. The data portal through which these kind of data will be aren't yet fully available, but will soon be available. You can get the QR code here. And if you're interested in some of the papers that I've highlighted, they're open access and you can access them here as well. And with that, I'll be very happy to take any questions. Thank you very much.